RTSA is a shoulder replacement procedure in which the natural anatomy of the ball and socket joint is reversed, implementing a ball-shaped prosthesis on the scapula and carving a socket prosthesis into the humeral head. This procedure is becoming increasingly more popular each year, as it was reported that there were 30,000 operations of this procedure done in the year 2012, and this number has only continued to rise with each year. One downside of this procedure is the high risk of postoperative complications, with up to 68% of patients experiencing some degree of postoperative complication. This can be anything from acromial fractures to hematomas and infections. Our team worked with Dr. Augustus Mazoka's research lab in the Musculoskeletal Institute at UConn Health to aid them in their research, which was aimed at investigating various forces within the body when an RTSA implant is utilized. Our group's goal was to provide some additional insight and support to their efforts through proposing possible testing design improvements, as well as an antibody modeling and analysis of the human shoulder.
Before our design team began assisting the UConn Health research team, they supplied us with data they had collected from previous tests using native shoulders. Here you see a video playing of abduction in a native shoulder using the simulator. Cables are attached to the muscles and a tensile force is applied to them via an actuator, which causes the shoulder to abduct. As shown in this graph that UConn Health created, the amount of force from each muscle that is required to abduct the shoulder is recorded and summarized. Drawings of each muscle are shown to give you an orientation of where each is anatomically. The second portion of our design project focused on using the UConn Health simulator to analyze the stresses in the scapular spine during RTSA shoulder abduction. This video is from one of their previous RTSA tests. During normal movement, muscles contract and pull at their origin and insertion points. This was important to replicate in the test as the deltoid's origin on the scapular spine, lateral clavicle, and acromion process causes stress in these areas when the muscle contracts. It is believed that the scapular spine fractures caused by RTSA are due to the increased tension it creates in the deltoid and the resulting increase in stress on the scapula. The previous experimental setup only pulled from the deltoid's insertion point on the humerus. Although this was sufficient to gauge abduction angles, it did not replicate the true forces acting on the scapula during abduction.
This video demonstrates the antibody model we generated to replicate the Musculoskeletal Institute's shoulder simulator. On the left, you will see the anterior and posterior views of the 3D rendering of the model's right shoulder. On the top right, you will see the force output from the 3 deltoid fibers that were modeled at the Musculoskeletal Institute. And on the bottom right, you will see the force output from the supraspinatus muscle fibers. This simulation is of a patient with a massive tear to their rotator cuff, with only the deltoid and supraspinatus muscles active. You will notice that the force output curve will continue to rise as the abduction angle reaches 60 degrees. Here is a closer look at the force output curve of the deltoid. The red line represents the posterior deltoid fiber, the black line represents the medial deltoid fiber, and the blue line at the bottom represents the anterior deltoid fiber. Notice that the anterior deltoid fiber is not recruited in the simulation. The net force output from the deltoid is approximately 200 newtons. This graph represents the force output from each of the 6 muscle fibers that model the supraspinatus in any body. The net force output from the supraspinatus here is approximately 67.5 newtons. In summary, the deltoid and the supraspinatus need to exert a total of approximately 267.5 newtons of force to abduct the shoulder 60 degrees.
So after doing some of our research in Anybody and at UConn Health, we wanted to make the actual design. We started with this full model of the glenohumeral joint, but quickly found out it was far too complex for SolidWorks. Kind of working with those complex geometries just doesn't work well. Didn't really help much. So we moved on to a one-dimensional version of the shoulder. This is really just a hinge joint, and all we want is pure abduction of the shoulder anyway, so we figured this was a close enough approximation. Now here's our first alternative design. It used just one fiber and one actuator. And that kind of little red square up top is essentially the deltoid of the humerus, and the pulley on the bottom would be the insertion point. So this gets us a really good picture of the forces going on in the deltoid, but we quickly need to kind of scale up the number of fibers to better approximate it. So here is a design we actually had working at UConn Health. One pulley, 3 fibers. This didn't really work well either, mainly because we found there was kind of catching between the different fibers as they move through that single pulley, and we can definitely assume there's an increased amount of friction there. So moving to our final design, we just have 3 separate actuators with 3 separate pulleys on the bottom. This kind of reduces that friction, reduces the catching, and it also gives us a better picture of all 3 fibers while freeing up space on the humerus for other attachments we needed to complete the project.
In conclusion, our team was able to conduct antibody modeling to create a computer model of the active forces in a native shoulder through certain movements, particularly the abduct motion, which provided very similar results to the UConn Health, giving us high confidence in our results. We also were able to create a final design of a pulley system that could be implemented in UConn Health's testing, which we believe would be the most accurate method for testing the deltoid of a shoulder with an RTSA implant.